So in the last video we discussed about homomorphisms and the first isomorphism theorem and somewhat about what an isomorphism really is. In this video we are going to do a bit of a different thing, and we are going to think about conjugation as a change of basis. Okay, so just to recap, what a conjugation is that for any element x in G, you can write its conjugate with the element small g in capital G as G x G inverse, and I'm going to write this as psi sub G of x. So it's just a notation that I came up with. Um, so this means the conjugate of x using the element G, right? And we want to look at what conjugation essentially does, right? So say that G is acting on a set S, which is essentially just the set of first n numbers, right? And so it's every element of G is essentially a function. So let's try to think about what the function x does. Maybe x is doing something like this. It's a cycle 1 2 3. That is, it sends 1 to 2, 2 to 3, and 3 back to 1, or something like that. So it could really just be anything. We don't care. But yeah, so you have 1 2 3 all the way to n, all these elements, and then x is going to do something to these elements. So maybe like 2 gets sent to 1, 1 gets sent to 2, maybe like 3 gets sent to itself, something, I don't know, maybe n gets sent to n itself. We have no idea, right? So in general, you can write this sort of mapping as a permutation. So every element can be thought of as every element in the group can be thought of as just a permutation. So let's say that, like, I don't know, for simplicity's sake, that x is a 3 cycle. That is, it sends 1 to 2, 2 to 3, and then 3 back to 1, right? So x is represented as this cycle 1 to 3. And let's say that G is something that's very simple. It just swaps 1 and n. So G is just a permutation that sends 1 to n and n back to 1, right? So okay, so what we are going to do is just sort of, figure out what's going to be the result for any arbitrary element when we pass this conjugation on it, right? So first it's going to do a G inverse, which just happens to be the thing. So you know what, actually let's take G to be a slightly more complicated thing. Let's say that it's also a 3 cycle and does this thing. It does 1 2 and n, right? So it sends 1 to 2, it sends 2 to n, and it sends n back to 1. So first we want to apply G inverse and then x and then G to any element on the set S, right? So let's say you have the elements 1 2 3 so on, right? All of them, and okay, so let's not sort of write it in this order. Let's rewrite it in a slightly different order. So we know that what element is going to get mapped to 1 by finding the G of one thing, right? So G is this thing, then G inverse will essentially just be something that sends n to 2, because 2 was sent to n. So okay, so it sends 1 to what? It sends 1 to n, and then it sends n to 2 and 2 back to 1. That's what G inverse is, right? Okay, so what we want to do is just apply G on each of these elements, and that's going to tell us what is actually going to get mapped to these elements, right? So G of 1 is just 2, so 2 is going to get mapped to 1 when we do G inverse, essentially. So G inverse does this thing. Okay, I'm gonna make this slightly smaller. So the first mapping that we are going to do is just G inverse, and then we are going to do x, and then we'll do G again. So 2 gets mapped to 1, right? So 2 is g of 1 and then it gets mapped to 1, just easy. Um, what does get mapped to 2, right? So that's g of 2. So g of 2 is n, so n gets mapped to 2, and then 3 gets mapped to 3 and so on. But eventually what's g of n? It's 1. So 1 gets mapped to n, right? Yeah, and then you do this x thing. So like 2 actually goes to 2, but then that 2 is actually going to go back to, you know, whatever g of 2 is. So g of 2 is actually n, so this gets this is actually going back to n, right? And g of 3 is 3, and then so on. So g of n is 1 and this thing is 2, right? So these two are essentially the same, right? Yeah, so if you think about any element, how it's flowing is that, so let's say you're thinking about the element 2, right? It gets renamed. So G inverse renames it as something, let's say 1, and then it goes to some other element which is just another, and then which is just the renamed version of n essentially. So what's happening is that 2 is actually being sent to n. So so to go from 1 to 2 you do g, and to go to 2 to 1 you do g inverse. So similarly over here you're doing g, and n to 2 is g inverse, right? So all of these elements, they are renamed to these elements via g inverse, and similarly all of these elements get renamed to these elements via g inverse. So what we're actually doing is more or less just renaming all of these elements as something, then switching them around, and then unrenaming them. I don't know how to pronounce that, but you get it, right? Like switching the labels to whatever they were before, right? And so the way that we rename the variable is through the operation g inverse, right? So whatever x is doing is actually like not happening on these elements, but more or less on these elements instead, right? Because these are like just, so one is just 2 in disguise, 2 is n in disguise, and so on. And so how do we find that what is 1 actually representing, like at the base level? That's just g of 1. So say x is this permutation 1 2 3, right? That's what x is. Then gx g inverse, what this does is it renames every element via g inverse, then it does x, and then it renames with you know, g basically, or unrenames with g essentially. Yeah. So x is actually not operating over 1 to 3 anymore, because 1 to 3 are just like the new labels for whatever the previous things were. And how do you find the previous things? Well, it's just the inverse of this operation, which is g of 1, g of 2, and g of 3. So x is actually operating over these elements, and it's the way it's operating still remains same, but yeah, the elements in S change, right? And so what we are seeing is that if x is some permutation, right, let's say like 1 2 3 4 5 something, whatever, and g is, well, any function or any permutation, then gx g inverse is just g of 1, g of 2, g of 3, and then like g of 4, g of 5, so on. So what a conjugation really does is just it changes the basis, right? Yeah. So everything, like every property that we would be interested in, like the order of the element, or maybe like the size of some group generated by the element, or something like that, right? All of that remains the same. It's just that the naming is different, right? Yeah. So that's like the conjugate of one particular element. What about the conjugate of a whole group, right? So you consider a whole subgroup, let's say. So H is just a subgroup in G, right? Then we are thinking of, renaming the elements in, so G is like acting on, let's say, S, right? So you rename all the elements via some permutation G in G, right? So you do like G inverse of S, and so what G inverse of S essentially means is like, in this, you don't think of the S thing as a set anymore. You are here thinking of it as a list. So I'm just going to call it S sub L, like, to represent it's a list now. So you do G inverse on each of the elements of that, right? So you rename all of these. Then you do whatever operation from H you want to do, and then you do G, right? So essentially whatever operations were happening in the subgroup H, they are still happening. It's just that now they're acting on a different thing. So G, so like H acts on S, right? The conjugate of H, so G inverse, is now actually going to act on G of S, right? If that makes sense. So yeah, I mean, it acts precisely the same way, right? It's exactly the same, except that it's now, the numbers are different. So what we can say is that G inverse is isomorphic to H, and the isomorphism is like pretty easy to see. So for all H in capital H, this isomorphism, it just sends it to G inverse, and you can see that it's an isomorphism. Firstly, it's a homomorphism because psi of GH1, psi of GH2, that's just like GH1 G inverse, GH2 G inverse is equal to GH1 H2, G inverse, which is just psi of H1 H2, right? So it's a homomorphism, yes. And it's like injective because, if GH1 G inverse is equal to GH2 G inverse, then there's only one way that this actually happens, which is like, you cancel this, you cancel that, you cancel that, you cancel that, so just H1 equal to H2. So it's an injective homomorphism, which means it's an isomorphism. So every conjugate of the group is basically the group itself, with just the set on which it's acting renamed by a little bit, right? So all of these different conjugates of the subgroup, they're called, so all of them combined is called like the conjugate, you see, class, essentially. Not for the subgroup, sorry, for an element, yeah. Okay. So that's how you interpret conjugations. Now that we have already like defined the conjugate of a group and all that, and we have been using this so far, I think it's a good place to define this very important thing, which is called the inner automorphisms. It's a big name, but you'll see it's actually very simple. So this psi sub G is a function, right? And it acts on the elements of the group G, right? So what we can do is we can define all of the different functions like this, which are conjugations, and then make a set out of them. So that's something that we represent as in of G, which is the set of inner automorphisms. It's a heavy word really, but it's just some set for now. So it's just all of these functions psi sub G, such that G is in capital G, right? So first thing that I claim is that this, and obviously you have the operation of group, you just have the group operation of function composition. So what I claim is that, and this thing actually acts on the elements of G itself, right? I shouldn't actually say it like this. It is supposed to be G to G or something like that. Fine. Yeah. So, okay, that's the correct notation. Okay. So what I want to do is show that this is a group, firstly. So how do we think about the function composition of, say, psi G1 and psi G2? Well, we just think about what's going to happen when we apply this on some element x, right? X is in capital G, obviously. So this just gives us, psi g1 of g2 x g2 inverse. But then this is just g1 g2 x g2 inverse, and then g1 inverse, which is just g1 g2 x g1 g2 inverse. You can figure that out. So it's just psi of g1 g2 x, right? Yeah. And so this is clearly in the group G. Sorry, in the group. I shouldn't even say it's a group for now. I should just say it's a set. So there's closure. There's obviously the identity. So the identity would just be psi sub e, because that's like doing nothing. So that's just psi of, yeah. So it's just psi sub e of x. That's just like ex e inverse. That's like just x. So if you had like psi g psi e of x, then psi e of x is just x. So it's like just psi g of x. So we are saying that psi g psi e, that function composition, that's the same thing as just psi g for like any psi g in the set in of G, right? So far we have proved that, there's closure, there's an identity element. We also have to show that there's inverses. So psi g inverse is obviously also in of G because of the way that it's defined, right? So for all small g, you have this thing, small g in capital G, obviously, like, yeah. Right, so psi g and psi g inverse, these are inverses because we already showed that psi of g1 psi of g2, that's equal to psi of g1 g2, right? So then psi of g inverse, you combine them, that's a psi of g inverse, which happens to be psi of e, which is, well, just the identity. So just e sub in of G. I don't know how to write that. I'm just gonna call it 1 for now, right? So psi of G and psi of G inverse, they are inverses, yeah, for any small g in capital G, right? So the inverses also exist, and that means that this thing is a group, all right? So this is actually, so in of G is actually a subgroup of another bigger group, which is a more general thing, which is called the automorphism group of G. So the automorphism group of G is basically all of the isomorphisms from capital G to G itself. So just to sort of recap, what an isomorphism is a homomorphism which is injective. So homomorphism that goes from capital G to G, and it's supposed to be injective, and yeah, which now kind of means that like the whole codomain has to be covered. So it's also surjective. So it's a bijection essentially, and so that's a isomorphism and all that. But yeah, so just have, let's say, some function that takes you from capital G to G, and it's a homomorphism. So that we're just saying like psi of x y is equal to psi of x psi of y. It's easy to see that like something like a conjugation is obviously just an isomorphism, which is not the identity function. So there are like isomorphisms which are not the identity function, which take you from one group to the other group, right? And so that's not the only that's not the only way that you could have the isomorphism, right? You could have very, very different ways of this happening. So all the different isomorphisms that you could have, combine them all, put them in a set, and then function composition is the group operation. That thing is what we call as aut of G. This is also a group, and let's actually show that it's a group. So you take any isomorphism psi 1 and isomorphism psi 2, you multiply them, then that's another isomorphism, and it's easy to show like this on x times y. That's just psi 1 of psi 2 x times psi 2 y, but then that's just like psi 1 psi 2 of x times psi 1 psi 2 y, because of the way that homomorphisms work, and both of these are in fact homomorphisms. So we just showed that psi1 psi2 is certainly a homomorphism, and obviously it's injective, because if psi1 psi2 of x is equal to psi1 of psi1 psi2 of y, then you can cancel this thing, right, because of injectivity. But then you can cancel this thing as well because of injectivity of, psi1 and psi2. So that means x is equal to y. So then psi1 psi2 as a whole is also injective. So it's an isomorphism. So we have shown closure so far. So psi1 psi2 is also in automorphism group of G, right? If psi1, so I should say for all psi1 psi2 in the automorphism group. Yeah. So closure is there. Is there an identity? Yeah, there is. The identity isomorphism, that is, we do nothing, right? The do nothing isomorphism, if that makes sense. Like the way we defined conjugation over here, you could write it as psi sub e, right? That's the identity isomorphism. And notice that the psi over there, and so psi for the inner automorphisms and the psi over here, these are different notation. Yeah, I should probably use a different notation over here to just, so that like you don't get confused. So let's use phi over here, right? So psi sub e is the conjugation with e, obviously, and that's a isomorphism from G to G, which is what we call an automorphism. So an automorphism is just isomorphism between the the group itself. So you have G isomorphic to G, obviously, with the do nothing isomorphism, right? So this is a way to do it, but so is any other conjugation, and so is any other automorphism. So any isomorphism that goes from G to G, that's called an automorphism. You just have a set of all of that, that's the automorphism group. So we have not proved it's a group so far, we have proved closure. We also have to show that's identity, and this is the identity. It's like obvious why that's the case. Now we also have to show that there's inverses, right? Okay, so just to sort of recap, phi from G to G is automorphism if psi is isomorphism. Yep. Right. And so aut of G is just a set of all automorphisms of G. Okay, cool. Now we also have to show that the inverses exist in aut of G, right? So for any psi, I shouldn't say psi, let's just say for any phi in so for all phi in aut of G, what's going to happen is that is that phi inverse is also an automorphism, right? Is also an automorphism, and we can show that very easily. So this is not a big deal. Yeah. So okay. First we have to show that it's a homomorphism, right? So we start with the fact that phi is an homomorphism. So like phi of x y is equal to phi of x times phi of y. But then, since phi inverse is a bijection, I mean obviously phi is a bijection, so phi inverse is a bijection. So you can write x and y as phi inverse of something. So just phi inverse of A, phi inverse of B, and that's equal to phi of phi inverse of A is just A and B, and this happens like for all AB. So for all AB you can write this equation like without really caring all that much, and then you can multiply this by phi inverse, and then this just gives us phi inverse of AB. That's equal to phi inverse of A, phi inverse of B for all AB, so it's clearly homomorphism. And phi inverse is a bijection, so it's a bijective homomorphism. What is that? It's an isomorphism. So there's closure. Not closure. So the inverse, phi inverse thing, it also is an automorphism, and so for all phi in aut of G, phi inverse is also in aut of G, right? So far we have proved closure, identity, and the existence of inverses. What about associativity? I mean, come on, it's just function composition. So So yeah, um, so automorphisms are defined now. So are inner automorphisms, and it's like pretty obvious that this is a subset of all the automorphisms, and it's a group. So it's a subgroup, and I think this is a good place to stop. So I'll see you guys in the next video.